Okay. Yeah. Hello, everyone. So we we will have some lectures on still on chapter 7. I hope we can finish this week. So today and Thursday, and we still have one more. At least one more week before the final exam week start, right? At least still have the next week. And also your TA will be also your last TA will be last week, I think. So our chapters we will finish on chapter 7. Okay, chapter 7. If you look on your textbook, actually I planned initially we will finish on chapter 8, but only just a few sections on chapter 8 because it's not really uh, that long for chapter 8. We only have the arc length and the surface area. Okay, but let's see if we can finish chapter 7 within this week. I can give you a little bit chapter 8. Okay, a little bit chapter 8. Because the idea on chapter 8 is actually similar with the integral. Yeah. Anyone asking? From the online students, do you want to ask or do you have any questions? You raise your hand. Yeah. Or is it accidentally pressed? Okay. Perhaps I will give you a little bit idea on why what we will learn. Okay. So chapter 7. This is all the techniques of integrations from integrations by parts, trigonometric integrals, trigonometric substitutions, partial fraction. I think we will finish partial fraction today. And there are some sections that mostly it's strategy exercising. It's basically we can skip and just focus on practicing. So the next one is actually approximation of integral, which I will also skip that because we already mentioned at the beginning. So some methods I will skip, and we finally got to have the improper integral. Perhaps this will be the last. Okay? But if we have a chapter 8, this will only include two sections, okay? The arc length and surface area of revolution. And probably, okay, if we don't really have much time to be in the class, I will provide an additional video about the chapters and also the exercise. I will provide maybe 3 or 4 videos, okay? And also for review, preparing your final exam as well. Okay. Uh, if if I look at if we look at the chapter 8, this is actually still about the integral. This is just an overview, so you have some idea on what happens. Okay. In integral, we have uh, this area under the curve, right? The arc line means we are going to measure how much length this is, how long this is, okay? How long the curve is, and still it's the idea A, B. Uh, this is just an overview. I will let you know later for more details. But the idea here is if you have a tangent line somewhere, maybe here, okay? Let's say that is our tangent line. And let's say that it's very, very small, okay? We will have, in this case, is dx and dy, okay? We have a 2 components. And the components that is on tangent, let's say that is a dl, okay? So basically, we know that from the hypotenuse, we know that, right? Or even we know that this is the square root of this, okay? And we can exchange this, okay? Become, let's say this is 1 plus dy squared and the x squared, okay? Or this become 1 plus dy over dx. And this will be our dl. We can write something as that. And how to take this into our measurement? We are going to use the integral. That's just a brief intro. I will explain later. Okay. And the other part is the surface area. The surface area is, if you rotate this to here, okay, rotate uh, to the x-axis, rotate the curve. If you rotate, you know that we will have a volume, right? But we will also have the area, okay? So we can calculate the surface area. So basically that is what we are going to achieve. Both methods we are going to achieve through some integration techniques. So that is just chapter 8. Chapter 8 is actually having a 5 or 6 sections, but I think the most important one is just the first one and the second one, which is the arc length and the surface area. Okay, but I will let you know if we have this in our final exam or not. Okay, by this week. Okay. So that is the chapter 8, just a little bit overview. So we have done the by parts, integrals, strict subs, and hopefully today I can have a partial fractions finished and maybe some intro to improper integral. Okay. Okay. So before we are going to go more details, maybe we can have some sort of review on the questions from the last Thursday. So the question is, find the volume obtained by rotating the region bounded by the given curves rotated about the specified line. Volume is something pi. So you need just to write the uh, the numbers or the constant. So if we draw the curve is minus x squared plus 6x minus 8, y equals 0, rotate about y-axis. So if you look here, the curve is having this this curvy line like that, the blue line. And if we rotate through the line y axis, then if you imagine first, you can imagine taking the disk, okay, which is weird and it's not solvable by disk, right? We cannot solve it by the disk method. So the only way we can solve this is through the shell method. So we can use shell. And the idea behind the shell is we need to identify which one is the radius, which one is the height, okay? So the radius here is just x, I think, right? And the height will be the curve itself, right? And the other line is y equals 0 here, right? So we just write the curve itself. So we can write down, this is the idea, a little bit calculations, a little bit calculation here and there. You need to also to find the endpoint through the intersection, okay? Find the root of the curve, and then plug in all the numbers. There's a little bit calculation here, and I think you see that some constant is canceling each other, and we know that the answer is 4 multiplied by 2, it's 8. Okay, so I think nothing really complicated aside from the calculations. Okay, aside from the calculations, and the identification is, I think, also not too difficult here. Okay, because the rotation is just a y-axis, right? Okay. Oh, by the way, if you want to factorize quadratic easily, sometimes I'm using the table, and you can exchange and try some factors here. Okay, and to know whether you are confirmed it's correct or no, you can cross multiply and then find out whether it is the middle constant or no, it's the same or no. Okay. Okay. Next part is this. Okay, we need to integrate this. Okay. There are some trials which one you are going to take. Okay, and if you look at, we have 1 plus x and then squared. Okay, I think it's better to have this as an own element, like the 1 over 1 plus x squared, and the other one is x e with power of x, because e, we can put e in terms of derivative or integrations. We may need some trials here, and I think the best case is if you want to use, if we're using the u as x e with power of x, and the phi is 1 over 1 plus x squared. Okay, and then we set up our integration by parts, and by looking at this, we can simplify that and cancel the 1 plus x, right? We can cancel the 1 plus x, and then we can have this calculated easily. Okay? And then we can put 0 and 1 into our calculations, and we get the answers. Okay, the answer is half e minus 1. However, I will give you some thought, okay, or other process that probably maybe important. Okay, if you look at the integrations, okay, it has squared at the bottom, okay, in the bottom equations. if you consider this as a quotient rule in derivatives, if you have f over g, if you derive this, it will have f prime g minus g prime f, and this will be g squared, okay? Now, if we let our g is our 1 plus x, it has squared here, and let's say we have this. And also, we can imagine what's happened for the top equations, okay? What is the previous form, okay? This is a little bit trial and error, but you can start with e to the x. Okay? We can start with e to the x. And we can try to derive this e to the x over 1 plus x. And it has e to the x 1 plus x, and then minus e to the x for the g prime becomes 1, right? And this is g squared. And then a little bit calculations, and we see that this is our original question. Okay, so sometimes figuring out with some advanced guessing, do some trial, maybe it will be having more faster approach. Okay, rather than using the techniques, the integration by parts or any other techniques that you can think of. Sometimes try some guessing, maybe give you better results. And then you can directly putting all the information and you get this. Okay? In the exam, for my case, if you try this method, that's okay. That's really nice, because sometimes this method is pretty much helpful. Okay. 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 Okay, we can move on to, I think last one we have discussed this. Okay, we have the trigonometric substitutions. So now we will discuss the partial fractions. Okay. Okay, first, we consider these two fractions. Okay, let's combine these two fractions together. So do some calculations. X squared plus 2x minus x is plus x, and then minus 2, and then the equation here will be x plus 2 minus x minus 1. Okay. And we can solve this. 2x minus x is x. 4 plus 1 is 5, so it is x plus 5. X squared plus x minus 2. Okay. Now, the idea of partial fraction is came from, if we have a big chunks fractions like this one, okay? If we separate this, become these two elements, and we integrate, it will be much, much easier, right? It's more simple, right? So if we take this as an example, so if we have this as a question, first thing we need to have, we can think this big fractions, and we need to think how to separate this. Okay, first, because you know that this is already in a from a two factors, so probably we will have two factors, right? We will have two factors. So probably this will result, or if you want to make another calculations for just a fraction itself, that's okay to distinguish between the algebra and the integral. So we can solve this first, find the two separate equations. And this is how you usually do it. Okay, so we have this, and we have a constant here. Okay, let's say A and B. Okay, let's say A and B. And what we are going to do is we are going to do the first process, the combinations part, and then try to figure out on the top equations. And we need to equal this top equation with the left one. Okay, so the right one will be equal to the left one. So this will be A and x plus 2 plus b and then x minus 1. This should be equal with x plus 5. And we have these equations. Now, to solve the problem, we need to group all the elements of the variable and the constant. And we will have a system of linear equations. Okay. So a plus b is 1, and 2a minus b is 5. We can solve this. And you get b is minus 1. Right? Or another way of looking at this, we can take this at x equals 0. So the equations become 5 equal 2a minus b, but still it is just this one, right? It's just a correction. But sometimes when you have the system of linear equations, you can take x equals something, maybe 1, 2, 3, and usually taking this x to make something in the process 0, maybe it will simplify. Okay? But otherwise, we can just solve the system of linear equations. Okay, because this is just a simple equation. We get a is 2 and b is minus 1, which is perfectly similar with our first process, 2 and minus 1. Okay, so that's actually the idea. However, throughout the process, there will be some cases on what kind of fractions we will have. Okay, what kind of fractions we will have. Okay, so first, if you can factorize the bottom part of these equations, you can factorize, and probably those factors will be determined on how each fractions will looks like, okay? And you can add a constant at the top equations, and we need to find the constants. Okay? That's the idea. Okay, so that's the idea. So separate the equations, find a constant, and then don't forget the question is still asking. We need to integrate. Okay, so we need to integrate each of the elements. So integrations of 2 over x minus 1 and dx minus integration of 1 over x plus 2 dx. And we get this is 2 ln x minus 1, and this will be ln x plus 2 plus c. Okay. Okay, I will give you like each sections by a practical example, so you can imagine how it turns out to be. So another example, okay, another example. If you take the integrations of x cubed plus x, okay, x cubed plus x, and then over x minus 1 dx. Now, if we imagine uh, the fractions as f of x over g of x, or maybe not fg, maybe p over q for rational functions. So if our functions defined as p over q, sometimes we can change this into this form. If you remember in a polynomial in your high school, probably, the r is called the remainder, right? If the division is not completely zero, then it will have the remainder, right? So the idea here is if the p degree is greater than q degree, which means the polynomial degree, okay? Then one way to solve this is we can use the division, long division, okay? So we can use the long divisions. Start with x squared. And then plus x. So plus, plus, so it's 2x and plus 2. So the functions become, or we can write the whole thing, x cubed plus x over x minus 1 is equal x squared plus x plus 2 plus 2 over x minus 1. Okay, and if we take the integration, I think you can integrate each one. Really simple, okay? Really simple. Okay. The next case is Okay, let's say this is our polynomial, and in our rational functions, we have to express as a sum of partial fractions. We can have a over ax plus b with power of I. We can have more and more, or as ax plus b in over x squared plus bx plus c in power of I. Okay, so if Q is a product of linear factors, let's say Q of x become a1x plus b1, and then a2x plus b2 until some k. Let's say that is our case. Then we can write b over q into a1 Okay. So in the first case here, no factor repeated. Okay. So every A1, A2, A3, it is a different factors from one another. Okay. So, for example, if you have integral of x squared plus 2x minus 1, this is 2x cubed plus 3x squared minus 2x dx. Now, first thing is we look on whether the equations can be factorized or not, okay? Especially the bottom one here, okay? And then we can factor out x, and then probably we can factor out the element from 2x squared plus 3x minus 2, right? Okay, so we can have x 2x squared plus 3x minus 2. And then we can try to factorize. Okay, right? 4x minus x, 3x, okay? So we will have at least x plus 2x minus 1 plus x plus 2, and we will have a, b, and c. Okay, and because if you find later a, b, c, and it's a constant, we can also integrate easily. This part become all element here becomes ln, ln, and ln, right? With a constant, And how to solve and how to find the ABC is practically similar with the previous one. We can have some calculations, and we need to solve the system of linear equations. Okay. That's the first case. Okay, the first case. So this is case one. Let me write case one. Okay, case one. Okay, let's going to have case two. Now in case two, we will have a repeated linear factors. So it will be A1, let's say A1 over, so this is P of X over Q of X. So A1, this is AX plus P1 plus A2 AX A1, this is A2 plus P2 plus dot 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 plus, let's say until some R. Okay. Oh, sorry. Should be repeated. Sorry, should be same on all cases, but different. Let's say until 3. So we call this as the linear factors. Okay, linear factors. Okay, perhaps it will be much easier if I explain in the form of exact fractions. Okay, if you have x cubed minus x plus 1, this divided by x squared and then x minus 1 cubed. Okay. This method will give you perfect alignment, a perfect alignment that is, if you imagine first, let's say we have separate these two, okay, to give you a brief idea on what happened here. If you have a quadratic on the bottom, the top equation should be having ax b, right? And we have a cube. You will have cx squared plus bx plus d, sorry, plus dx plus e. Okay. Now imagine you are having breaking down this into two parts. Okay. So ax over x squared, we can write in terms of a over x plus b over x squared, right? Okay. Still applicable to here, right? So basically, whenever we have a factors that is repeated, we can also divide. For example, we have x squared and then x minus 1 cubed. We will have five fractions. We will have 5 fractions. Okay. So the first one will be, let me write here. The first one will be x plus, this is x squared. Okay. Second one will be x minus 1, x minus 1 squared. Okay. And then the last one will be x minus 1 cubed. And the top equation will be perfectly a constant. Yes. See from here, we can change here. Simply the same way with this one. Yes. Okay, so this is called the repeated linear factors. Repeated linear factors. Okay, and the rest is pretty much similar. Okay, we need to find the find the constant A, B, C, D, and E. And still, if the question is usually this is integrations, right? Integrations of the x like that. We need to lastly we need to integrate all of this. Integrate, integrate, integrate. Okay, that is case two. We call it repeated linear factors. Okay, now case three and four. Case three first. Okay, we will requires that is if we have p over q, if our qx is let's say a quadratic, and if the value for this, we call the determinant, if you remember, is less 0, means the roots is imaginary, okay, imaginary numbers. Then we will have, okay, we call irreducible factors, meaning we cannot factorize anymore. Okay. For example, x squared plus 1, x squared plus 4, this is irreducible factors. So how we are going to separate this from our big fractions? So if we have x divided by x minus 2, x squared plus 1, x squared plus 4, first we can divide became each own fraction with the factors, the irreducible factors. And the top equations will be A. And for the irreducible factors, we will write Bx plus C linear and the x plus E. Okay. And then after we find the constant for A, B, C, D, E, if we find, then we still need to solve if we need to integrate this. I think the first one is easy. A over x minus 2, we can have ln, right? The second one and the third one, we have some equation with x squared plus 1 or x squared plus 4. The initial idea, if you have maybe a good numbers that you can substitute, you can use the substitutions method, or look at this x squared plus 1. What kind of integration if you have 1 over 1 plus x squared? If you integrate that. So if you have integrations 1 over 1 plus x squared dx, what will be the tangent inverse, right? Tangent inverse. So to solve this, we need to have tangent inverse. Okay. Okay. So before I'm going to solve the other one, this um, the x squared plus 4. Before we try to figure out how, let me just remind you with the tangent inverse. Okay. So tangent inverse x. Okay. If we derive, this will resulting in 1 over 1 plus x squared. Oh, forget plus c. Okay. Now let's try tangent inverse. If we have x over 2, okay, and we derive, this will result 1 over 1 plus x squared over 4, right? We need also to multiply with the chain rule x over 2, derive x over 2, which is half, right? Okay. And solve a little bit here, rewrite the form, it will be 4 over 4 plus x squared, right? We multiply 4 by 4, right? We can have 4 divide 4 plus x squared and multiply with half, and we get this is 2 over x squared plus 4, right? So this is 2, but we have 1. So we need to multiply with half, right? To get to 1. So this means that this is half tangent inverse of x over 2 plus c. Okay, so we can have a general formula, okay, for integrations dx over x squared plus a squared. Okay, this will have 1 over a tangent inverse x over a plus c. I think we can have 5 minutes break. Okay, 5 minutes break. Okay, we continue. So we continue a little bit. Okay. Uh, I think tonight I will give you some practice and exercise from chapter 7, mostly for 7.1 until the partial fractions. Okay, and maybe some part from 7.5 and 6 because it's probably still the same technique of integrations. Okay. Okay. Uh, this is case 3. Case 4 is the same as case 3. We will have also the irreducible factors, but we will have a repeated. Okay. So it will be similar to our repeated linear factors. Okay. So we will have a1x plus b1. Okay, it's pretty much similar, but the difference, this is a quadratic that is not cannot be factorized. So we have example x cubed plus x squared plus 1. Let's say we have these factors. And how we treat them as our linear factors. So we can have our repetitions. First, a over x plus b over x minus 1 plus, now this two is our irreducible factors, right? So we can write down. And mostly we will have the irreducible factors, that is the quadratic for our semester. So this will be a linear on the top and quadratic on the bottom. And we will have 3 repeated irreducible. So first one is this. Second one, okay. Okay, so a lot of fractions here. This is just an illustration, okay, just an illustration to show you that whenever you find any repeated linear factors, or in our case here, we have the irreducible factors, that is the quadratic one, x squared plus 1, and it has q. We can separate this into 3 forms, which is x squared plus 1, x squared plus 1 squared, x squared plus 1 cubed. Okay, and the idea to solve this long fraction is still the same. We are going to find a, b, c, and all the constants. Okay. Okay, and I think that will be the partial fractions. So you have an idea to separate the fractions into small fractions. If you can also think to use long divisions whenever the degree on your numerator is greater than the bottom one, the denominator, or you can think or look the bottom equation whether it can be factorized or no, and then you can have a linear factors, you can have repeated linear factors, you can have also irreducible factors. And how to solve it? Basically, you need to include all the all the technique of integrations, okay? But mostly, okay, mostly the if you have the linear factors here, this is probably become became the ln, right? If you integrate, and the one that has x squared plus 1 here, it will be probably the tangent inverse, okay? And the rest you need to figure out with some techniques, okay? Okay, so that will be the partial fractions. If we need some practice or maybe some solutions, I will provide, maybe next week I will provide within the additional videos. Okay? I've just uploaded, I think last night, some practice for chapter 6, okay? Especially the area and the volumes. Okay? Okay, now the next part in our chapter 7 is we call the improper integral. Okay, this is on 7.7 on your textbook. Okay, 7.7. Generally, in general, we have two types. Okay, two types of improper integral. The first one we call the infinite interval. That is this type. The second is discontinuity. Okay, so the improper integral is a way to approach. Anyway, this means that it is definite integral when you have your endpoints as large as possible, or if your interval, you have some discontinuity in between. And throughout some process, we may at least find some finite results, okay? Although it's having either infinity or some discontinuity and at the middle, okay? That's why it's called improper integral. It's not like properly integrated, but we need to approach them with limit, okay? With limit, okay? So we will have to use limit concept to solve this. Okay, as an introduction, let me just giving you the graph of okay, let's say this is our 1 over x squared. Okay, okay, let's say this is 1. Okay, this is 1. And I want to know the area, like if we have area under the curve, okay, of 1 over x squared dx. But I would like to evaluate from 1 to infinity. Okay, to start with, can we integrate the infinity? The answer is actually no. But okay, but if we take a look, if we observe the area under the curve, okay, this is from 1. Let's say we have some variable here. Let's say t. Let's choose t here. T can be any number, can be 100,000, but let's say it's t here. Okay. If we take these integrations as our functions of t for the area, we take the integration. We can write down that this is 1 over x, minus 1 over x. And we put 1 and t. We got that this is actually 1 minus 1 over t, right? Okay. Okay. Now imagine you have t. And when you put the t maybe larger, you increase the number of t, maybe 10, 100, thousands, really, really big. Remember in our limit concept at the beginning of our course, we can have this as 0, and we will get at least 1. Or, logically speaking, uh, no matter how large t is, okay, this area will be less than 1. Okay, at least. Okay, at least. If we have maybe 0.000 something, at least we will have a is less than 1. But then if we are using the limit, let's say we have the limit as t approaching infinity, and we write like this. Now we can do some calculations, okay? Because we have the limit concept. Okay? So we will have and with the limit, the answer is 1. It's a finite result. And when we get the finite result, we call this result as a convergence or convergent. Because it's converged into one finite answer or one exact solution, which is 1. Okay, that's 1 over x squared. Okay, to compare this 1 over x squared, let's compare with 1 over x. Let's compare with 1 over x. I will write in the next section, so you can write this introduction first. Okay, so let's graph the 1 over x. Say this is 1. And the idea is still the same. That is, let's compute the integration from 1 to infinity of 1 over x dx. Okay, since we have applied the limit, let's try the limit within this 1 over x. Now we will have ln t minus ln1, or in our case here is ln t, because ln1 is 0. Now if you look at the ln, when it's reached the high number, the answer to this will be it's going to have an infinite, right? Infinite numbers, right? Or we call that this will be a divergent. Because it's diverged, it's not converged into a finite result. Okay. Now, if we compare and why this happens, if you look at the visuals, you can try it. If you have a graphing device or try on the website, look at this. Okay. 1 over x, if you look at the graph, it still has some gaps. Okay. Which is if you look at the very right on your graph, if you have a graphing device, it's not really that close to the x-axis. If you compare with the 1 over x squared, this has a quite close gap when you try to maximize your x value, right? And it turns out that because of this is having some power, if you remember the difference between the power and without the power curve is having more. If it's increasing really fast. If it's decreasing really fast. So that it's reached close to x-axis faster than the 1 over x. Okay? And you can also imagine the exponential, which is really, really fast. Okay? Okay. Okay, now that's the introductions. And as part of introductions, we can have some definitions, okay, some definitions for the type 1 integrations, which is the infinite intervals. Okay, if we have a, t, and fx dx, if this integration exists for every number that is t is greater or equal a, then the integration from a to infinity of f of x dx will be equal with the limit as t approaching infinity of this integration from a to t of f of x dx. And provided the limit exists, okay, provided the limit exists. And B, if you have integrations from t to b f of x dx, if this integration exists for every number that is b is greater or equal t, then the integrations from negative infinity to b of f of x dx is equal limit as t approaching negative infinity t b f of x dx. Now, of course, we need also to provide it the limit also exists. Okay, and we call the integral of a to infinity f of x dx and negative infinity to b f of x dx. We call them convergent or divergent. So convergent is if limit exists, and divergent if limit doesn't exist or tends to be an infinite number. And also if we have integrations from, let's say, from negative infinity to infinity, we may have that. Okay? if we can separate, become two separate integral. Okay. So the next one is if both integrations from a to infinity and we have also this two both converges or convergent, then we can have you can take this into two integration and we can take limit for each integral. Okay, take limit for each integral. And this a is a real number. Okay. Now we have the type 1. Okay. The idea is if you have the integral that is having infinite interval, you can do limit and changing the infinity with any variables and approach those variables with infinity, with limit. Okay. Okay. Now back to the, if you remember the previous or the beginning of the improper integral, we have this and this, right? This is converge, right? And this is diverge. Now, can we probably initiate some formula, okay, general formula or general rules? Let's say we have 1 to infinity of 1 over x with power of p. Okay. So from this general formula, p is any numbers. Okay. We can look and take the limit and then we try to integrate this. X with power of p is the same as x minus p, and we can have the integrations become x 1 minus p over 1 minus p, and then from t to 1. We can factor out the 1 over 1 minus p because that is the constant. Okay, and this is limit with approaching infinity, and we will have this is x t with 1 minus p and 1. This is minus 1. Or we can write this as one over t p minus 1, right? Now from here, we can imagine what kind of p that we will have, okay? So if p is greater 1 or p is less 1, okay? If p positive greater than 1, okay, we will have uh, converges value, which is, let's say we have 2, for example. That will be a convergence value. So for the positive one, uh, p minus 1 is greater than 0. So we will have 1 over xp is equal 1 over p minus 1, okay? Because of the negative. Because if we take it minus something here, it will be a negative. So we can have exchange. And this part will be, we can eliminate those parts. So this part will be 0. We still have negative 1. Negative 1 goes here. And that's why it's 1 over p minus 1. So if p less than 1, so p minus 1 less than 0, so if we look at t, 1 minus p, okay, and as t getting large, okay, t 1 minus p is also getting large, right? It's logically, and we can call them is also is diverge and his converge. Also, if you take p equal 1, it will be also diverge, right? So equal 1 also diverge because it will be 1 over 0 here, right? So that will do. So p greater 1 will be converged, p less equal 1 will be diverge, okay? If we may be taking different integration, but is similar uh, p values here, maybe we will have a different values, okay, if we change a little bit. Okay, so probably that will be some questions regarding this p value. So if I change the integration and you need to find um, in general what intervals or what kind of p that is converged or diverged. Okay, so this is how you answer. Okay, if you want to find general rules, okay, within these integrations, p values. And how to integrate is basically all the techniques you learned before, and we can use that also for integrations. The improper. Okay. Improper. The problem in improper integral is we having the infinity or some point will be undefined, and we need to approach those with a limit. Okay. Okay. Let me give you some example, and then maybe we can end in our course today. So I will evaluate these two integrals. So these two questions, I think we can solve with substitutions, right? Okay, I'll leave you these two examples. You try to work out by yourself using the improper integral and some substitutions method. Okay, and maybe I will review this afterwards next for this Thursday. I just go to type 2, okay, definitions, type 2 improper integral. So type 2 is a theorem, okay, the theorem. So if a functions f continue on a, b, like that, and this continue at b, okay, then the integrations we will have limit from the left of b, and we need to change those b with t. So we need to have a left hand and right hand limit for our case. And if our functions continue on open A and then close B, and it is discontinue at A, then we have integrations from A to B of f of x dx will be equal to as t limit as t approaching A from the right. Okay. This is t, this is b f of x dx. And of course, these both are correct provided the limit exists on both cases. Also, if a function has discontinuity at C, okay, and then A less than C less than B, and you know that we have A C f x dx and C b f x dx. Both are convergence. Then we have A b f x dx is equal which means you need to have each one of this has having a limit, okay, having a limit. Okay. Okay, what does that mean in our case here? So you have our functions. This is maybe A, this is B. If this is having a discontinuity like that, okay. So of course, if you are approaching the limit from the left of B, it's still possible, right? Because we have continuity here, and we approach the limit from the left of B. Similarly with A, when you have discontinuity at A, we can approach this from the right of A, right? The limit. Okay. So that's why we have this limit we need to have to change the value that makes the functions discontinue with some other variables, and we try to make the limit constant, left hand or right hand limit. Okay, so the idea is in the improper integral, if you need to compute, you need to compute the limit. Okay. There is one more section on this improper integral, which is the comparison theorem, but I will let you know that we will have those parts on this Thursday, okay, this Thursday class. So I will end our course up until here, okay, and we will have a little bit of feedback time for today's class. Okay. Okay. I think we can try. Okay. I think we can start. Okay. Okay. 3, 2, 1. Okay, it's ready. Okay. Okay, good. Okay. Okay. Okay, calculus is difficult. I agree. I agree. Okay, number 2. Get ready. Okay, you need to write the result in a fraction. Okay, in a fraction. Okay, 3 minutes. 30 seconds, 3 minutes, 30 seconds. I hope enough to find. Okay, 1/12. Okay. Yeah, you don't need to write the pi. Okay. Sorry. Oh, okay. Calculus is difficult, but you get it right. Okay. Question 3, the last question. Okay, I hope enough time, around 4 minutes. Okay. Yeah, continue. Yeah. Should be from last week, last Thursday class. If you want to check your notes, last Thursday, I think. Okay. 20 seconds. Okay. Okay. Still okay. Majority correct. Okay. So whose calculus is difficult in this classroom or and the online students? Can you write down your ID? Okay, I got your ID. Okay, calculus is difficult, but still you can answer the question. Good. Okay, so hopefully you guys have learned some of chapter 7 today, and hopefully you get to know more about integrations, okay? Because this converse diverse situations will be also our discussion next semester. So, and it will be more a little bit complicated than this semester. So hopefully you guys understand on the most of the chapter 7, and we can have a continuation on next Thursday, this Thursday, before we have a little bit break time, holiday, New Year. Okay, so after New Year, still many exams for a final exam week. We still have at least 1 week for class next week. Okay, our quiz. Okay, remember we still have quiz chapter 6. I think it will be better on Tuesday, next Tuesday, next week Tuesday, because after the quiz, I can review more on preparation on your final exam. I think that will be better. Okay, and let me know whenever you find difficulty on questions on or practice in your textbook. Okay, because I know that yeah, calculus is difficult. Okay, uh, if you learn in the next year or the third year, still calculus is a foundation on most subjects, especially in engineering. Okay, so yeah, I think see you uh, Thursday. Okay, see you on Thursday. Okay, wait for a minute.